We have already discussed that continuous time Fourier series is used to find out the Fourier spectrum or frequency domain view of periodic signals. We are trying to express the given periodic signal as a linear combination of harmonically related complex exponentials. That is the main idea of continuous time Fourier series. In real life, we are encountered with so many aperiodic signals. For example, speech signal, which is an aperiodic signal, right? And how to find out the Fourier spectrum of aperiodic signals, or how to extend the ideas of continuous time Fourier series to find out the spectrum of aperiodic signals. That was the motivation of continuous time Fourier transform. So before that, we have to go to a key concept in which Fourier thought that a periodic signal can be considered as a periodic signal. You will have a confusion now. Now you will have a doubt. How can we express both of them as same? See, periodic signal is different, aperiodic signal is different. But through a beautiful mathematical concept, Fourier said that even a periodic signal can be considered as a periodic signal with some certain assumptions, some mathematical assumptions. That is what we are going to discuss in the first video. So let us go into the video and check how a periodic signal can be represented as periodic signals.
Okay, so we have discussed in the previous classes that the LTI systems or linear time invariant systems has a particular property that is known as linearity property. So what is meant by linearity property? Linearity property says that the LTI systems obey the superposition principle, right? So it obey the superposition principle, right? So this we have discussed in detail in the first unit and the second unit, right? So what is the advantage of this linearity? So because of this linearity of the linear time invariant system, it has a specific property. What is that? We can express any input signal x of t as a linear combination of fundamental signals. Let us say we can express any arbitrary signal x of t as a linear combination of impulse signals, right? We can express it as a linear combination of impulse signals, or we can express it as a linear combination of step signals. We can do like that. So what's the speciality of that? What is the advantage of that? See, if we can express the input signal as a linear combination of fundamental signals, then we can express the output signal y of t as a linear combination of response of those fundamental signals. So you have to keep this in mind, right? So if you are expressing the input signal x of t as a linear combination of impulse signal del of t, then you can express y of t as a linear combination of the impulse response h of t. So this is the advantage of doing like this. So this is what we have discussed in the first unit and second unit, right? And when we come to the third unit, we are trying to express any signal as a linear combination of complex exponential, right? So what we have discussed in CTFS or continuous time Fourier series, in continuous time Fourier series, we have discussed that we can express any periodic signal. So you have to keep this in mind. We are trying to express any periodic signal as a linear combination of, so linear combination of e power j k omega 0 t, right? So what is this linear combination of e power j k omega 0 t? So this e power j k omega 0 t is nothing but it is the harmonically related, right? So harmonically related sinusoids or harmonically related complex exponentials, right? So any periodic signal x of t can be expressed as a linear combination of e power j k omega 0 t. That is what we have discussed in continuous time Fourier series. So if you don't remember that concept, I request you to go back to the continuous time Fourier series videos and recall the concept, right? So the basic concept is that any periodic signal, so this word is very, very important, right? So we are discussing about the periodic signal only in CTFS, right? So periodic signal, any periodic signal can be expressed as a linear combination of e power j k omega 0 t, where e power j k omega 0 t is the harmonically related complex exponential. So in real life, all signals are not periodic signals, right? There can be a periodic signal also. For example, some signals will be looking like this, right? Something like this, right? So some speech signals right? So it will go for sometimes and it will stop like this, right? So we cannot expect that all the signals we encounter in real life are periodic signals, right? There are aperiodic signals. Mostly the signals we encounter in real life in the analysis of signals and system are aperiodic signals. Now the problem is, how can we extend the idea of continuous time Fourier series to find out the spectrum of the aperiodic signal, right? Aperiodic signal. So that is what continuous time Fourier transform is trying to do. Continuous time Fourier transform is trying to find the frequency domain view, right? So the frequency domain view of the aperiodic signal, because we know about periodic signal and continuous time Fourier series of periodic signal, right? So that is only about periodic signals, but in real life we are experiencing or we are encountering so many aperiodic signal. Aperiodic signal means which is not repeating, which is not everlasting signals, right? These are coming for a shorter duration of time and it will stop. That kind of signals are known as aperiodic signal. Now what is the frequency domain view of this kind of signal? That is what the continuous time Fourier transform trying to say. The continuous time Fourier transform says that how can we express any aperiodic signal x of t as a linear combination of, right? So linear combination of e power j omega t. So that is what continuous time Fourier transform is trying to say. How can we express any aperiodic signal? So this word is very, very important, right? How can we express any aperiodic signal as a linear combination of e power j omega t? That is complex exponential signals, right? So here there is no k here, because it is not about harmonically related complex exponential. In continuous time Fourier series, the definition is perfect. The periodic signal x of t can be expressed as a linear combination of harmonically related complex exponential. But in the case of continuous time Fourier transform, it is not like harmonically related complex exponential, but it is something else. That is what we are going to see in the upcoming videos. Now, how we arrived into this concept, how Fourier came to the conclusion that we can express not only the periodic signal but also the aperiodic signal as the linear combination of complex exponentials. So that was the key contribution of Fourier actually. So Fourier thought that an aperiodic signal like this, right? So here we have an aperiodic signal x of t. So he thought that any aperiodic signal x of t can be considered as a periodic signal. Now you will have a doubt, how a periodic signal x of t can be expressed as periodic signal. So we can do one thing. Let us take the aperiodic signal. This is the signal x of t, and what he said is that we can replicate the signal in an interval t0. So what he did is that this is the actual original aperiodic signal. What he did is that he has replicated the copy of this aperiodic signal at an interval of t0 like this. He has replicated the copies of x of t at different time intervals t0. Here you can see this is t0 and this is minus t0 and this is 2t0 and this is minus 2t0, right? So this here comes the half of that, right? So that is t0 by 2. So he said that let us express the aperiodic signal x of t as a periodic signal by copying the replicas of the x of t at different intervals of t0. Now you will have a doubt, and he called it as x of t0 of t, right? He called it as x of t0 of t. So this is saying that actually it is an x of t but with replicas at an interval of t0. That is the meaning of this idea, right? So it is expressed as x of t0 of t. Now he said that let us assume that we are pushing the other replicas to the infinity, right? So we can push these replicas to the positive infinity and these replicas to the minus infinity, right? That is what is idea. Let us push the replicas. So let us push this replica and this replica to the infinity, right? Can you imagine that we are moving this particular replica and this replicas, all the other replicas to the infinity. We are moving this to the negative infinity. So then you can see that who is remaining here? Only this aperiodic signal is remaining here. See, you can see that the other replicas are going to the positive infinity and negative infinity. So what is only remaining? The only thing remaining is x of t. So he said that any aperiodic signal can be considered as a periodic signal provided we should say that the replicas of that signal is at the infinity. Otherwise, we can say that it is periodically repeated, but the period is infinity, right? The period is infinity. That is what is idea, right? We can express it as a periodic signal, but period, see, the T0 is going to infinity. Now, as I have pushed the replicas to the positive infinity and negative infinity, so what you can see is that I am hiding that replicas because it has gone to the infinity, right? Now you look into this periodic signal and aperiodic signal. Now look carefully. This is equal to, we have made an aperiodic signal from the periodic signal. How? We have pushed the replicas to the infinity, right? The replicas located at T0 and minus T0 are pushed to the infinity. So mathematically we can write it like this. So what is the mathematical equivalent of that? Limit t tends to infinity, limit T0 or the fundamental period tends to infinity, x T0 of t is equal to x of t. This mathematics says that if we allow the T0, the period of the signal is at infinity, that means the next replica is repeated at infinity. So if you allow that, we can say that x T0 of t is equal to x of t. So in other words, we can consider an aperiodic signal as a periodic signal with a time period T0 is equal to infinity. That means that its replicas are repeated at infinity. So this was major idea of Fourier to find out the frequency domain view or Fourier transform of an aperiodic signal. So I hope this concept is clear for you. Based on this concept only, the Fourier transform is derived. In the next video, we are going to discuss about the mathematics behind this idea.
I hope the idea was clear. We can express aperiodic signals as periodic signal by assuming that the period is infinity. So we are extending the replicas of the periodic signal to the infinity. In that case, we can express or we can consider aperiodic signals also as periodic signals.